So in this, I'm going to talk about a visual guide to delegate authorization (PKC) in a zero trust cryptographic ecosystem. In the physical world, you have a user, you have a wallet attendant, you have your ignition unlocked and a drive enabled, you have a limited wallet key. Trunk is locked, failed, restricted access. But in the digital world, you have a user, you grant access token, then you have a read profile, API access, data pathway, verified access, denial, restricted operation. Auth 2.0 allow user to grant third-party application specific limited access to the data without ever sharing their actual credential. Four distinct roles interact to separate identify from access: resource owner, authorized server, port 3000, the security authority, the resource server, the port 5000, the vault, the port 4000, the wallet. These four distinct actors communicate across public network, relying on a cryptographic proof rather than the direct trust. Each node is strictly bounded by what it holds and what it trusts. The primary role: client type, orchestrate user generally. Auth server issues cryptographic tokens. Resource server protects the API, what it holds. Client type, temporary tokens. Auth server, private signing keys, PKS and a user data. Resource server, protected resources and a user data. What it trusts: client app, the user input. Auth server, cryptographic verifier. Resource server, only the auth server signatures. Temporary cryptographic assets govern the lifecycle of access. Authorization code, lifespan, seconds, purpose, exchange immediately for tokens directly with the server. Access token, JWT, lifespan, sort of 15 minutes. Attached to HTTP header as a bearer token to unlock specific API. Refresh token, lifespan, long lived, purpose, stored securely by the client to request new access token when old one expires. The authorization server acts as the ecosystem sole security author input. Authorization server autonomy output: authorized token, internal engines, RS 256 private key, PC verify, hash engine signed, JWT access token, dot well known JWKS JSON input. These servers verify the identities, validate PKC challenges, and sign JSON web token using a private RSA key. The client application orchestrates the journey without holding the secrets. The input: user clicks login, receives code at a rollback. Client app anatomy: you have an internal engine, you have a PKC generator, you creates a random code verifier stored in a temporary and HTTP only cookies. Hashes to the code challenge: you have an output which is like the token exchange request. Get request with authorization bearer header. Operating in a hostile public environment like a browser, the client dynamically generates cryptographic proofs rather than relying on a static password. The resource server acts as an independent cryptographic vault. Input: resource server autonomy. Output: intercepts API profile carrying bearer token. Internal engine: the JWT verifier, issuer, audience, expiry, signature, and express scope. Servers JSON payload returns 401 and a 403 error. The resource server never communicates directly with the client to verify access. It mathematically unpacks the token locally using the auth server's public key. So this is important. So the resource server never communicates directly with the client to verify access. It mathematically unpacks the token locally using the auth server public key. Tokens are mechanically unlocked and verified by the GWS loop. So auth server fetches matching public key from .well-known JWKS JSON token header view. Resource server catches incoming access token, reads unencrypted header. Public key mathematically scans and unlocks the token signature. Public keys are broadcasted openly, and any API can independently verify a token authenticity without ever seeing the private signing key. The PKC ensures the app claiming the code is the exact app that requested it. The lockbox setup: client app, code verifier, code challenge, SHA 256, auth server. The interception: authorization code. The third is the verification: authorization code, code verifier required, authorization one no, or either the code authorization code, client app, code verifier okay. Proof key for code exchange: PKC neutralizes interception attacks by dynamically binding every request to a one-time cryptographic secret. The PKC handshake establishes the trust across untrusted challenge. The first is initiate. Client says user to auth server with a code challenge. Authenticated: user logs in securely at an auth server. Authenticate: user logs in securely at an auth server. It redirects. Auth server sends user back to client with an auth code. Exchange: client sends auth code plus code underscore value directly to the auth server. Exchange: client sends auth code plus auth directly to the web server. Issues: auth server verifies the hashes and return an action token. Consumes: client sends access token to the resource servers to fetch data. This precise sequence ensures secret never touch the user browser, and tokens are only issued to the mathematically proven initiator. The diagnostic matrix for common architecture failure: 404 bad record. The root cause is the PKC validation failed, code reused, or redirect URI missed. Architectural fix: ensure code underscore verifier cookie persisted in login and callback. Error code hosts JWT verify error, JWKC endpoints returning a private key instead of a public key, only export public keys SPKI format to the well-known JKS beacon. 401 invalid token expired, wrong audience or a forged signature, ensure resource servers audience precisely matches the intended client. 403 insufficient scope, valid token but lacks specific permissions, request exact scopes during the initial authorized redirect. Auth 2.0 is fundamentally a zero trust ecosystem. The client never sees the user password. The resource server never trusts the client app. The authorization server does not even trust the client to keep a secret. Client app, no trust, user password, world, resource server, cryptographic trust. Inside, the entire architecture is designed to operate safely inside a completely hostile public environment. The production grade implementation rely on a strict operational hygiene. Strict validation, resource server must verify signature, expiry issues, and audience log. We never rely on the client. While model tools like Auth or AWS Cognito abstract the code, securely configure the architecture requires a rigorous understanding of the underlying cryptographic flow. Minimize lifespans. Access token must remain stored live. Example 50 minutes to minimize damage if leaked. Rotate and revoke. Refresh token must be handled carefully. Rotate upon use and bends to mandatory HTTP TLS protocols.